In this video, I'm going to review the questions in the midterm to review. So I'll talk about solutions for all the questions that are listed in the midterm to review. Okay, let's get started with first question. The first question is about the stability for linear time invariant system. So we have three stability we talked about before. One is BIBO stable, one is marginal stable, one is asymptotic stable. Okay. So this question asks for the verification if a linear time invariant system is stable or not. Okay, so the given linear time invariant system given is as follows: I have x dot t which is equal to 0 to 2 negative 2 0 0 0 negative 0 0 0 0. So this is a matrix. You can consider this as a matrix A. This is B. And this is C. Okay. So to check the BIBO stable, you can do two things. If all my eigenvalues of A have negative real parts, okay, if that's the case, now you can just say BIBO stable. Okay. Now in this case, the eigenvalue, because this is diagonal matrix, so eigenvalue just be negative 2, negative 2, 0. Apparently one of eigenvalues does not have negative real parts, so we cannot say direct from there. Okay. Of course, if one of eigenvalues is positive, we can also not say anything because it could cancel out for the BIBO stable. So if that's not the case, we have to check this. We have to compute the transfer function. The transfer function is given by C time Si minus A inverse time B. So C is given here and AB they're given there. So when I compute the transfer function to check is the pose of every term of my transfer function should have negative real parts. If that's the case, well, it's BIBO stable. If not, it's not a BIBO stable. So once we plug in the A and B and C into this form, we can calculate according to what this one says. So there are a couple of steps. I don't want to go to the detail of the steps, but if you plug in your A and B and C over here, you get C is this and B is this. So let's plug in this number over there. So Si minus A is just S time identity. So identity is a 3 by 3 matrix. It is a 1 0 0 0 1 0 0 0 1. So it has to have the same size of my matrix A. Now when you do an inverse, you compute the inverse is just because this is a diagonal one. So matrix inverse just the inverse of each entry. Okay, then you put as also a diagonal matrix. By doing the computation, we can write this one stuff as this. So this is the product of first two. Then you do the product of this one time again this matrix B. So you can get the transfer function. So if you put them together, the transfer function is given by 4s plus 2 divided by s over s plus 4s plus 2 over s times s plus 2. So the pose, you only have one entry basically for the transfer function. So I basically want to check if the pose of this transfer function, which is this, have negative real parts. So which is the pose you set the denominator here to be 0, which means I have s times s plus 2 be 0. Now the poles are just 0 and negative 2. Because this one does not have negative real parts. This one does, but this one does not. So it's not a BIBO stable. Okay, so for marginal stability and asymptotic stability, we just need to check the eigenvalues of A. Okay, so the asymptotic stability says the linear time invariant system is asymptotic stable if the eigenvalues of A, which is here, have negative real parts. If that's the case, it's asymptotic stable. Otherwise, not. Okay. So if you check the eigenvalues of this A, so which is after calculation, because this is diagonal matrix, so eigenvalues are just negative 2, and 0. Apparently, one of the eigenvalues is 0. Does not have negative real parts, so it's not asymptotic stable. So for marginal stable, we have to check either the eigenvalue could be the case that eigenvalues have 0 real parts, or the real parts of the eigenvalues have negative real parts. Okay, so but for those ones with 0 real parts, we have to calculate the algebraic multiplicity and geometric multiplicity. Okay, so if you have any question, you can check my previous videos and the lectures about what are the geometric multiplicity and algebraic multiplicity. Okay, so for marginal stable, we have to check the eigenvalues. For negative ones, we're okay. We don't have to do anything. That's fine. Okay, for those ones with zero real parts, for this case, which means 0, right? 0, I have to check the algebraic multiplicity, which means how many eigenvalues are equal to 0. Okay, which means 1, because I only have one eigenvalue equal to 0. And I also want to check the geometric multiplicity, okay, which means how many linearly independent eigenvectors do I have for the eigenvalue 0. So here, because I must have the geometric multiplicity, so typically the geometric multiplicity has to be less than or equal to algebraic multiplicity. So you can have either geometric multiplicity equal to 0 or 1. That's the only case. You cannot be 2 or 3. Okay, which means I just to check if it's 1. If it's 1, we're good. If it's 0, it's not good. Okay, because for 0 eigenvalue here, I must have at least one eigenvector, non-zero eigenvector. Okay, that non-zero eigenvector will be, which means we have at least one eigenvector for this lambda, right? This eigenvector is linearly independent of itself, basically, of others, basically, right? For example, if the eigenvector, I don't consider eigenvector is 0, 0, 1, whatever value it is, it has to be non-zero, basically, right? So this one, I have at least this one is linearly independent, because this one is a linear independent of others, right? We could have a linear independent of the other one, so this one has to be 1. Okay, so the geometric multiplicity is also 1. So which means I have algebraic multiplicity and a geometric multiplicity has to be equal in this case. So we can say it's marginal stable. To summarize, you can also, so typically for BIBO stable, we have to check the transfer function and to see if the poles of my transfer function have negative real parts. If yes, it will be stable. If no, it's not BIBO stable. So marginal stability and asymptotic will only check the eigenvalues of A. If the eigenvalues of A are all have negative real parts, they are both marginal stable and asymptotic stable. If some of them have positive real parts, they're not marginal stable, not asymptotic stable. If some of them have negative, zero real parts, we have to, first of all, it's not asymptotic stable, for sure. And to check if it's marginal stable, we have to check the algebraic multiplicity and the geometric multiplicity to make sure they are equal. If yes, it is marginal stable. If not, it's not marginal stable. Okay. Now let's go to the question number 2. Number 2 is also to check the marginal stable and asymptotic stable. This is for linear time invariant system. Okay, so typically for linear time invariant system, it's a little bit hard to check the marginal stable and asymptotic stable. A lot of times you can just calculate the solution, assuming you have some initial condition, and then to make sure to check if a bounded, because a marginal stable asymptotic means you don't have the input, your input is 0, and it says bounded initial state. If a bounded excites a bounded state, what's a future state, is called marginal stable. And asymptotic stable, first of all, it has to be marginal stable plus the final state goes to 0 as t equal to infinity. That's called asymptotic stable, basically. Okay, so if I do look at this one, so if we check this system, this one, so if I can, this is a basic definition of marginal stable and asymptotic stable. Okay, now the end of that, I just have to find a solution to see if this is the case. Okay, so what I'll have to do is trying to figure out what the solution to this one, assuming that I have some initial state x1, 0 and x 0, of course. So here, this one, according to what I have over here, so this is a 2 by 2 matrix, so my x must have a 2 dimension. It's like vector is x1 t, x2t basically. Okay, so let x to be x1t x2, so we have x2t, so we have two basic equations. So first one is x1 dot t equal to negative x1t plus e1 half t x2t. So I do this one product. Okay, x2t will be, according to here, is just negative t times x2t. Okay, to solve for the solution, apparently the first one is a little bit hard to compute, because to compute x1 I have to know x2t, right? So we can start with the calculation of x2t. So fortunately the x2t can be calculated fairly easily, okay, because it's only a ODE by itself. It's just a function. X2t dot is negative t times x2t, which means, yeah, I just have I can solve for the solution. So if you put x2t to the left hand side, okay, do the derivative is equal to negative t, and we can integrate both sides of okay, you basically time dt on both sides, and you do the integration. You have this. When the integration on both sides, you get the integration of 1 over x2t over x2t is just a natural log of x2t, and this integration of negative t over t is negative 1 half t squared. Don't forget this have a c constant, okay, because I don't have lower bound upper bound, so this is a c. Okay, I have a constant value over here. So which means my x2t is e to the negative 1 half t squared times e to the c. Of course I can see this is just a constant value. Okay, so this is nothing but constant. By using initial state value x20, assuming I have initial state x20, so I can compute x2t is just x20 times e to the negative 1 half t squared. So that's the solution for x2t. Once I figure this solution, I can plug this one into the first one, and I can figure a solution for the x1t. Okay, so by plugging in, so if you do the x1t, so I plug in x2t into a substitute x2 by x20, that's the solution I found, times e to the negative 1 half t squared. I have x1 dot t is negative x1t plus e1 half t times x20 times e negative 1 half t. So nice thing here is it just cancel out, because the product will be just 1. Okay, so I have the differential equation. The first one is just given by this. x1 dot t is negative x1t plus x20. So this one, you can solve this one by using the linear time x dot t. Using the x dot is ax plus bu. That's the we have. Of course, I can consider b to be 1, u to be this one, whatever we want to consider. So the solution for this guy will be just eat x0 plus integration from 0 to t eat minus tau, and I have bu tau d tau. That's my solution. So I just have to replace, do a kind of change. So here sort of we have a is negative 1, and I consider b is 1, whatever. U is just x20. Okay, assuming that's what I have. So this is also a constant. Okay, so if you do that, my solution will be just x1t is e minus negative t x10 plus integration from 0 to t e minus t minus tau times x20 times d tau. That's my solution. So I just go a whole bunch of steps. Okay, this is the steps I'm going going through. So the final solution is just given by e minus t x10 plus 1 minus e to the minus t times x20. So if we combine these two, this is the solution I found for x2t, and this is the solution for x1t. If I combine them together, I get the solution for the linear time variant system that I mentioned at the very beginning. Okay, so that's the solution over here. So in order to do this one, I have to check using definition. Right? Definition says the marginal stable means any bounded is any x10 and x20. Remember, this has to be any value. I should get a bounded x1t and a bounded x2t for any future t. So if you do this one for any bounded x10, x20, and x1t, x2, they are bounded, because this is bounded, this is also bounded, so and this is also bounded, so it's always bounded. So this is marginal stable. And the asymptotic statement says if it's marginal stable plus x1t and x2t will go to 0, right? For x2t, yes, it is the case, because as t go to infinity, this guy go to 0, so this product go to 0. However, for x1t, e minus t does go to 0 and the product also goes 0, but here it's not because e to the minus t goes to 0 and 1 minus 0 is just 1. So if essentially the final state will be determined by x to 0. It's not going to 0. That's why it's not an asymptotic stable. Okay. Question number 3. Okay, so this is about the controllability of a linear time invariant system. So here I give a linear time invariant system x dot t, which is this matrix time xt plus this matrix time ut, and y is, this is say the c. It doesn't really matter because controllability doesn't involve yt. So c is just this guy, this 1 time xt. Okay, I want to check if the system is controllable or not. So for given linear time invariant system, the very simple way you do is to use the controllability matrix. So the controllability matrix is basically given by b a b until a n minus 1b. So this n is dimension of x. Okay, so the x is dimension has apparently the dimension of x is 3, right? That's really because you do the product, it has to be 3, right? So the dimension is 3. Okay, so which means this for this case is just equal to b a b a minus 1, n is 3, right? N is 3 for this case, so it's 3 minus 1 is 2, right? So a squared b, so only have this 3, okay? So if you calculate that, so b is just given by 1, 1, 1, 2, 2, 2, and if you do a times b, so a times b, if you calculate this one, it's just 0, 0, 0, 0, 0. Of course, you do a squared b is also 0, 0, 0, 0. So your c will be just 1, 1, 2, 2, 2, stuff like that. So first of all, you can drop all zeros. They don't count. And also this is linearly dependent because 1, 1 times 2 just 2, 2, 2. So you can also drop one of those. So rank of c, okay, when I go back a little bit. So when I compute this rank of c, there's only one linearly independent column because the all others 0 you can ignore them. And 2, 2, 2 because the linear independent of 1, 1, 1, so you can drop one of them. Okay, of course you can drop 1, 1, 1. That's the same. So rank of c is just 1, which is less than the 3. Okay, so this is not controllable. The next question is about a controllability for linear time invariant system. Okay, so here's my linear time invariant system, which is given by x dot t is -1, 0, 0, -2 times xt plus e minus t and e minus 2t times ut, and yt is 1, 1 xt. So this is, you can see this is my c. Okay, of course this a and c are constant, but bt is time invariant, so it's still linear time invariant system. Okay. So for this one, for the linear time invariant system, we only have one approach to check to verify the controllability, which is computed by this W, T0, and Tf. So I will tell you, go to one step by step to tell you how we build this W matrix. Okay. Okay. The first step is to compute the transition matrix. Okay, it's transition matrix. So it's definition of transition matrix, but in this case, because this is diagonal one, so the transition matrix is just computed by the exponential of each diagonal entries over from tau to t over d tau. That's what we have. Okay, so if you do this one, so the transition matrix is given by this diagonal. So the first one is the -1 integrated from tau to t over d tau, and this guy is also from tau to t, but the only difference is -2. So doing integration, we have e minus t minus tau, okay, 0, 0, and this is e minus 2 t minus tau. This is my transition matrix, okay. So once you compute transition, next one you compute transition matrix time b tau, okay. Okay, so you time b tau. Okay, once we have that one, so we have, when we compute this guy, we have e. This is what we computed the transition matrix time b tau. We will change the t to tau. It's e minus tau, e -2 tau. So once we compute this one, is e minus t and e minus 2t. Okay. So next step is, okay, this one gets a little bit interesting. So this one w and t0 and tf. This is a matrix. You want to check the rank. If the rank has rank is the same as the dimension of x. So the dimension of x is 2, right? Because I have 2 states. So this one I want to check this WT0TF. WT0T is integration from T0TF. From this one is this guy inside here is basically this whatever you calculate over here. Time is transpose. Of course, I here what I do is I have phi. Once you have this one, you can compute this phi TF tau. Okay, so you just replace T by TF. Basically, you replace by T and TF. So this one is, after doing this one, you compute a TF. So this is phi TF tau. Sorry, B tau. You do a transpose. No, you don't do a transpose of that. And then here you do phi TF tau B tau. Do a transpose of that. Okay, that's what we have. So this is WT0TF is integration from T0TF of a phi TF tau B tau time phi TF tau B tau. The two terms do the transpose. Okay, so that's why I compute this one over here. Then I replace T by TF, which means I have E minus TF, E minus 2TF. I replace every T by TF. And then you do a transpose of this guy, which is E, you change the column to a row. Okay. So once you do that, you integrate from T0 to TF, you do the product. The product of the two is just given by E minus 2TF, which is this guy times this guy, first entry, this guy times this guy, second entry, this guy times this guy is third entry, this guy times this guy is fourth entry. You have it over here. So then you integrate over d tau. Okay. This integration is just integral with each component individually. It's the same integration of each component. Okay. Because this one is not a function of tau. This is a function of TF, right? TF. They are like constant if you consider tau as a variable. So the same as integration of you pull it outside integration for 1, right? 1 from integration 1 over tau from T0 TF is just TF minus T0. You have this guy, this guy, this guy, this guy. So that's the final this matrix. Okay. So what this says, if this system is controllable, the condition is the rank W, T0, and TF has to be equal to the dimension of A, which is x, which is 2. This one be for any T0 and TF has to be true. That's a condition for controllability. So if you check the rank, because if you check the determinant this guy is just 0, which means the rank of this guy, you cannot have full rank of 2. If it's a rank of 2, the determinant cannot be 0, right? So rank has to be less than 2, which means it's not controllable. Okay. All right. So next question, question number 5 is about observability of linear time invariant system. Okay. So here's a linear system time invariant system that I'm giving for question number 5. So the x dot t, which is this guy, this is A, this is B, and this is my C matrix. Okay. So for observability, to check the observability of a linear time invariant system, the simplest approach is you check the observability matrix is given by A is given by C, CA until CA to n minus 1. Of course, the n is dimension of xt. So for this case, it's 3, right? So this one is same as I want to C, CA, and CA squared, right? So if you do compute this one, this will compute C, CA, and CA squared. So C is 111,222. So I put it here. This is the first column. This is a C. This is a CA, because if time A got a 0, 0, 0, this is a CA squared. So they're all 0, 0, 0. So rank, apparently here, the rank, you can do the column rank, of course, right? They say column, okay, or you can do a row. It doesn't, the column rank and row rank should be the same. If you do the column, they're all the same. 1, 2, blah, 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 1, 2, 0, 0, 1, 2, 0, 0. So yeah, they are linear dependent. Only one of them is linear independent, which means the rank of O is 1, okay, which is less than 3, that I want to have the dimension of my xt. So this is not observable. Okay, so next question is about observability for linear time invariant system. So this is a little bit more complicated than linear time invariant system. Okay. So linear time invariant system, I also have. So this is my matrix B over here, BT of course. I also have typically I only have one approach that can verify if a linear time invariant system is observable. Okay, so it's given by this MT0TF. Okay, the computation is quite similar to the controllability one. Okay, for linear time invariant system. So first, still compute the transition matrix given by phi, tau, t, and tau. This follows the exactly the same method I mentioned before for the computation of the transition matrix. This is also transition matrix. So the transition matrix only matters for matrix A. It doesn't matter for B, T, and C. Okay. So the method follows the same approach because this is a diagonal one. So it's just exponential of integration from tau to t. So whatever you have over here, changing to tau, function of tau. Okay, because this is constant, doesn't change anything. And 0, 0, then this is also integration of e to the integration of tau to t of -1 over d tau. So if you do that one, you have this as a transition matrix. The next step is we compute c tau times phi tau t0, okay, which means I change t to tau, tau to t0. So if you change t to tau, okay, and tau to t0, so I have this one, right? You basically have changed this one to t to tau, tau to t0, okay, so tau minus t0, that's why I have this, that's the same basically, right? So the c tau is given by this over here, 1, 1, okay, so this is 1, 1, do it over there. If you do that one, you have this guy, okay, you compute this value. Now this m given by this is just given by this. This m is integrated from t0 to tf over d tau. That's the same as the controllability for linear time invariant system. So what I do over here, the first term is just the c tau phi tau t0 transpose. So that's the first term over here. This guy is just this term. You put it over here. Okay, so you have this. So then you compute the product of this two, right? This matrix is 2 by 1 times 1 by 2. So your product will be 2 by 2. So the first term will be this guy times this guy, and sigma this guy times this guy. Okay, and you do the same way. So actually you don't have to do more, but I want to still show you the computation of the results. So when you compute this guy, you do the integration. It's the integration of each components. Okay, it's the same as you do the integration. Move inside for each component, do the integration. The integration for each one for this guy, which is given by this, okay, is also given by this, right? This one I don't have. Let me correct one thing. So this is just -1/2. So they are all the same because the 4 are the same. It doesn't matter. They're all the same, right? You do the integration. As the computer gets the final result like this. This is the MT0TF is given by this. Now, because they are all the same, you don't have this is a column, this is a row, right? These two rows are the same. Of course, the rank is just 1. It's not 2 because they're dependent. The rank is less than 2, less than the dimension of xt because x has to be 2-dimensional. Okay, don't forget here I have xt is 2-dimensional, so this is not observable. Okay, so another approach, even this, okay, this is one approach you can use. Another approach you can look at this one is the observability of this guy is the same observability of I remove ut. If you remember in what I mentioned of observability, the observability you basically can let ut to be 0. The reason because I can let ut to be 0. Because it really doesn't matter. You don't have to change your ut. You just have to set ut to 0. The observability of these two will be the same. So which means that, hey, even if I have linear time invariant system over here, well, because I can let ut to be 0, so I can drop the entire term. So I can turn this one to be a linear time invariant one, even if I have a linear time invariant system, right? Because the ut really doesn't matter how it's like ut. So yes, it's same as the linear time invariant system. Now for this one, it's easy to check the observability. I can use the computer observability matrix, which is again is given by C and CA, of course, over here because only two dimension of my n is the dimension of xt here, which is 2, so which means my O originally has to be CA until CA minus 1. So n is 2, so you go from C until C times A. That's why I only have 2 terms, okay? So the C itself is a 101. So C times A, if you do C times A, so C is 101. A is -1, 0, 0, -1. So the product will be just -1, -1. So it's 1, 1, -1, -1 over here. So again, you see the rank of this guy, they're independent, they're dependent, because they're the same. So the rank of O is just 1, it's less than 2, so it's also unobservable. So this is much easier to verify, but a caveat will be, we want to make sure that this guy is constant. If they're constant, it's easy to do. If not constant, you still have to go back to the previous method I mentioned over here. You still have to compute the transition matrix, then you compute the C tau times phi tau T0, then you compute the matrix M T0 TF, which is integration of T0 TF of the product. This product, you take a transpose time itself, okay, then you integration that over tau from T0 TF, and to verify if this rank of this guy is equal to, you basically want to check if my rank of M, T0 and TF has to be equal to the dimension of xt for any T0 and TF. If that's the case, it's observable. If it's not the case, it's not observable. Okay, I believe that's all the questions for the review, for the midterm 2 review questions.